Hello everyone, welcome to the first lecture of week 6. In this week, we will explore differentiability of a single variable function fx, and we will give some examples as well as some basic definition of differentiability with using the right hand limit side and the left hand limit side. Once a function is continuous, it may be differentiable, but it is not a guaranteed that there is a continuous function is going to be a differentiability. But once a differentiable function, then it must be continuous function. That is the whole criteria of this week. We will explore some more theorems on differentiability, and we will see some examples where differentiability will be useful. So what is a derivative? The first questions we all asked. Derivative is nothing but derivative f dash of x of a function fx says how fast f changes with its argument, that means with its x. So if you have a function with respect to some domain x, then at one point how it changes fastly, that will give you a differentiability. So visually f dash x is nothing but it is the slope of fx at the point x, right? So if you find out slope here, you will see here this one, and this is a function here, and this is the tangent line. So once you have a tangent line, the slope is here, right? So if you take tan of theta, that will be the derivative of that function. That's all, right? So find out fx equal to 1 by 4x square, f dash of 2 equal to 1. Why? Because slope of fx at x equal to 2 here, see here, this one, tan of theta. So this will be how much? This will be 4 divided by 2. So this is equal to f dash of 2 equal to 1, because the slope of fx at x equal to 2 is 1. We can see this by looking at the tangent line to fx at x equal to 2. See this tangent line, and you will see that this is 2 by 2 is equal to 1. So similarly, derivative tells us how quickly something is changing, and in physics velocity will give you a derivative of a positions, right? So velocity can be used as and acceleration is the derivative of the velocity itself. So the double acceleration is the double derivative of the positions of a particles. In optimizations, we use the derivative are crucial for finding minimum and maximum value of a given function under the constraints, and there are several other examples. So now mathematically how we can derive the define the differentiability of a function. Let f be a real valued function defined on interval closed interval ab, and let a point c lying between a and open interval lying between a and b. So c lying between an open interval ab, right? So the left hand derivative of a function f at x equal to c, denoted by lf dash c, is equal to limit left limit c minus LHL. I believe that you remember this one, right? So fx minus fc divided by x minus c. So what you have to do, so fx is given for you in the domain, the point c is given to you, and you want to check that what is the derivative of this function at the point c from the left hand side. You will calculate firstly, this is the some value f of c. So you have to calculate the difference between these two numbers, fx and fc, and then you have to calculate x minus c here, right? So this is the same thing as we have derived in our first slides, where we will see we will have the slope of that number. So this is the slope, you see here. This is the differences between these two numbers, and then we have, right? So here doing the same thing. So we have to calculate f of x minus f of c divided by x minus. So this is the ratio of the differences between the function value as well as the argument value, and taking the limit from the left hand side will give you the left hand derivative. So left hand derivative of a function, right? Similarly, right hand derivative, take the limit value of those ratio, the difference ratio from the right hand side, it will give you the right hand derivative rf f dash c, right? And it is only happening if the derivative exists, right? So what is the derivable? A function is said to be derivable at x equal to c if its right hand derivative as well as the left hand derivative are equal. And that is the big conditions over a function is derivable or not at a given point x equal to c. You have to calculate first what? We have to calculate left hand limit as well as the right hand limit of the differences between a function value as well as the argument value. So that means if dash of c, that means the derivative of a given function fx, continuous function fx, is equal to at a point c is equal to the limit of the difference between fx minus fc and the ratio of x minus c. So remember this one. And if left hand derivative and the right hand derivative are not equal, we see that f is not derivable at the point x equal to c, right? So how we can write this one in a different way? So we can write x, let x minus c equal to h. So that means x tends to c, that means limit h tends to 0, right? And this is fx minus f of c divided by x minus c is equal to h. So you can remember this formula as well, that for a smaller value h, if h tends to 0, fx minus fc by h will give you a derivative. Now we can refine this formula as well. And how we can refine? We put fc or fx in the same value. So limit h tends to 0 and x minus c equal to h, therefore x equal to how much? C plus h, right? So we can write this one as c plus h minus of f of c divided by h. That is the most applicable formula for a derivative. What was that? Limit h tends to 0, f of x plus h minus of f of x divided by h. So this is the f dash of x. This is the formula for a derivative functions. Here it has written for f dash of a is limit x tends to a plus fx minus fa equal to x minus a. That is the left derivative in point a, and at the right end point b is equal to f dash b equal to from the right. So you will have a and b, the function is continuous in a closed interval ab. Then a function is derivable at the point a if we check or if the limit exists from the right hand side, and a function is derivable at a point b if this function is derivable or the limit exists from the left hand side. So here you can see here, right? Now a function f defined on interval closed interval ab is said to be derivable in the interval a closed interval ab if f is derivable at all points or each point of that closed interval. It may be noted that the function f will not be derivable in ab if it fails to be derivable even at one point of the interval. We give the relationship between the derivability and continuity of a function in the following slides. So a first example is so that a function fx equal to x square is derivable on 0, 1, right? So function is given as well as the closed interval ab is given. So a equal to 0 and b equal to 1 here. So let's choose a point c here, any point, not the midpoint, essentially a midpoint, any arbitrary point in a closed interval or open interval 0, 1. Then f dash of c can be written as f dash of c equal to what? Limiting value x tends to c, the difference between fx minus of fc divided by x minus c. So fx is given, fx is how much? X square, and fc equal to c square divided by x minus c, and here limit value is x tends to c. Now take this x minus c, so this will give you limit x tends to c, x plus c into x minus c divided by x minus c. X minus c, x minus c is cancelled out, x plus c. So what will it will give you? It will give you 2c, right? So f dash c equal to 2c. And since it is in the open interval, c lying in the open interval, So we can check at the end points as well. So we can going to check for f dash of 0, and by the definition of the derivative of a function at the end points, we have seen that we have to check the limiting value from the right for 0. So we have to check x tends to 0 plus fx minus f0 divided by x minus 0, f of x equal to x square and f of 0 equal to 0 square, so 0, and that is x. So the cancel out, this will give you 0, right? But look at the same scenario for the end point b. So we have to check from the left hand, from the left side of 1, right? So that means f dash on 1 is nothing but limit x tends to 1 by left side and fx minus f1 by x minus 1. So this will gives you x square minus 1 square by x minus 1. This will going to be x minus 1 into x plus 1 divided by x minus 1. X minus 1 cancel out, x plus 1 and x tends to, from the left 1, that will be going to be 1 plus 1 equal to 2, right? So that means here at the end point the derivative is 0, and the different end points 1, the derivative is 2. These two quantities exist and these two quantities are finite value, and for any point C between the open interval 0, 1, we have seen that is the 2C. So it is also a finite quantity, because between the number 0 to 1, each number is a finite quantity. So twice of that quantity is also finite. That means we have seen that in a closed interval AB or in a closed interval 0, 1, fx equal to x square has finite limits. So therefore the derivative exists for each point of this closed interval, and henceforth this function fx equal to x square is derivable in a closed interval 0, 1. Similarly, look at different type of the function. The function says that between 0 to 1, between here 0 to 1, between 0 to 1 where 0 is included is x, fx is x, and with 1 and everywhere fx is 1, right? So for this point it is fx equal to 1. Now we have to check whether the function is derivable on a whole real line R, right? That is the idea. So what are the critical points here? Now look at this here. In that first interval where the fx equal to x, it does not contain the endpoints 1, but in the second one, 1 is contained, right? So firstly we have to check derivability at x equal to 1. That means the idea is to check at the critical points first. So consider the derivable at x equal to 1 here, and we knew that we have to check the limit of functional difference of the functional value by the argumental value from the left hand side. So we have to find out limit x tends to 1 from the left hand side, fx minus f1 by x minus 1. What will be the value of from the left hand side? So 0 to 1, that is x. So the fx value is x, and what is the value of f1? It is x, so that is 1, right? Divided by x minus 1. So these are the cancel out, and what will be the limit value? Limit value is 1, right? Similarly, at the end points we have r f dash of 1, the left, this one, the from the right hand side. Why? Because in the second we have already x included x equal to 1, right? So from the right hand side fx minus f1 by x minus 1, and from the right hand side fx, what will be the value of fx? The value is x itself, but f of 1, f1 is equal to 1, right? So this will be x minus, no, so this will be wrongly written here. This will be wrongly written here. So I will give you here. So from the right hand side, you will see here, from the right hand side the value of fx equal to 1. So limit of x tends to 1 plus f of x minus of f of 1 divided by x minus 1. We can write this one, limit x tends to 1 plus f of x value is 1. This is the constant value, as you can see here, right? Minus f of 1 is also 1 divided by x minus 1. So what will be the value? That is equal to 0, because 0 divided by some number, so 0, right? So as you can see here, it is not derivable because the right hand limit or right hand derivative at the 1 is equal to 0, but the left derivative is equal to 1, right? So these are not equal, and henceforth the function is not derivable, right? Similarly, look at for modulus of x. Before going to take the derivative, can you imagine that modulus of fx is a continuous function or not? So for continuity, we have already seen that epsilon delta definition as well as the geometrical definition, where if the pen does not jump from the paper, then we will say that it is a continuous function. So for that, let us prove this. So for x greater than 0, the value is going to be like this, and for x is less than 0, it is also positive, so like this, right? So this is a continuous function, continuous everywhere, right? Including x equal to 0. But what will be the changes in the slope of that line? So as you can see, the line has the slope changes at x equal to 0. So now I am going to check whether our function fx equal to modulus of x is derivable at the point x equal to 0 or not. If it is not, what will be the right hand limit and what will be the left hand limit of that derivative? And if it is, then we will see that how it is. So calculating the limiting value from the left hand side. So from this side, x tends to 0 minus fx minus f0 divided by x minus 0. Firstly, f of x modulus, f of x is equal to modulus is equal to, it can be written as x when x is greater than 0 and minus of x when x is less than 0, isn't it? So that means I have to be very clear about our conclusion, right? And what will be the f0? f0 equal to 0. So at x equal to 0, it is 0, right? So f of x from the left hand side, this will be minus x. F of 0 is equal to 0 divided by x minus 0. So the value is minus 1. But calculate the right hand derivative for this. So taking limit x tends to 0 from the right hand side, what will be the value of fx? The value is x, right? And f0 is equal to 0 divided by x minus 0. So this will be cancelled out and the whole limiting value is 1. So now as you can see, from the left hand side it is minus 1 and from the right hand side it is plus 1, and henceforth both are different at the same point. So there cannot be two slopes at the one point, and henceforth the function is not derivable at x equal to 0, whereas the function is continuous at that point. Remember this one. So that means we have continuity at a point x equal to 0, but not derivable at x equal to 0. Can you imagine that if a function is derivable at some point x equal to 0, is it continuous function or not? Obviously it is. So it is not derivable at x equal to 0, but is continuous. So we will see in a minute or in a different slides where we have proved that continuity may or may not imply differentiability, but differentiability always imply continuity. So look at another good problem. Fx is derivable, we have to show that fx is derivable on a real line R, where fx equal to x square sine 1 by x if x is not equal to 0 and 0 if x equal to 0. This is also a very good problem. So consider the derivability at x equal to 0. We will find out f dash of 0, right, from the left hand side. So now you will have two things. You will have here as 0 from the, for this 0 value, f of this x equal to 0, and for other points, for all other points we have x square into sine of 1 by x, right? So we will directly find out its derivative. So x tends to 0, f of x minus f0 divided by x minus 0 by the definition or by the formula. So this will gives you f of x If x is not equal to 0, since it's a limiting value, so x is not equal to 0. Once it is not x equal to 0, this will give you a sign value, x square sine 1 by x, and f0 is value is given 0 divided by x minus 0. So this will be cancel out x, and this will comes out to be x into sine 1 by x. And in a minute, in the previous lecture, we have seen that limit x tends to 0, x sine 1 by x is nothing but it's a 0. So it's a finite quantity, and henceforth, if it is a finite quantity, it is a derivable as well. So the function f of x is derivable at where? At x equal to 0, and henceforth it is derivable on every r, on each point of the r. Can we show that this function is continuous? Obviously, yes. Any function which is derivable at some point, it must be continuous at that point. That is the idea of continuity and differentiability. So you can remember this one for your own concepts, that continuity may or may not imply differentiability. But differentiability always implies continuity. It's always implies continuity, right? So every differentiable function, so we have here every differentiable function, so this is a differentiable function, is a continuous function. Here is the continuous function. So continuous function. So continuous function is a superset of differentiability, and there exists some continuous function which are not differentiable. These are the questions, and these are open for you. Try to find out, and otherwise in the next lectures, or maybe some of the assignments, we will provide you the hint to how to solve these questions using the definition of differentiability and continuity, right? So look at some of the function. Can you show that this fx equal to 2x minus of modulus x is continuous function at x equal to 0, but not differentiable at x equal to 0? Let me try for you. And so we have here x equal to 0, and f of x is given modulus of x, right? Now we can calculate left hand derivative as well as the right hand derivative, and try to find out the limit of that function exist or not exist, right? So what will be the value of 0? So firstly calculate f of 0. F of 0 is nothing but 2 into 0 minus of 0 is equal to 0, right? So this is quite easy. So now calculate limit x tends to 0 minus f of x minus of f of 0 divided by x minus of 0 for fifth one, right? We are solving for fifth one. And what will be the value limit x tends to 0 minus fx? So fx is nothing but you can see here from the left we have fx is equal to 2 of x minus of x is equal to 2 of x plus of x, right? So here we have 2x plus of x divided by minus 0 divided by x minus 0. So how much this value? This value is limit x tends to 0 minus, this is 3x divided by x is cancelled out, so 3, right? And find out the right hand side, 0 plus f of x minus f of 0 divided by x minus 0. What will be the value for this part? That is x is greater than 0. So fx can be written as here, right? And this one is written as 2x minus of x only. So this will going to be x. So here we can write this one as limit x tends to 0 plus x minus 0 divided by x minus 0. So this will be 1. So as you can see, limit does not exist, as left hand limit is 3, which is not equal to right hand limit as equal to 1. So that's why this function fx is not derivable, What about its continuity? Check yourself that this function is continuous at x equal to 0. So this is the end of differentiability and its examples. Thank you so much.